Dear students, I am Mahesh Javalkar of Maratha Mandal Polytechnic, and today I am posting my second video on the DCT question paper solved of October 2020. Okay, so in this we will see a question number 21 to question number 40. Okay, so we'll start with the questions. The first question is, which of the following pin is used to demultiplex address bus and data bus when external memory is interfaced in 8051? Okay, so when we have studied the pins of 8051, we know that the address latch enable pin, okay, whenever it goes high, it will separate the multiplexed address and data bus. So it will demultiplex the address and data bus so that those lines are used for address first, because once if you get the address, then only you can go to that address and you can fetch the data. Okay, so first it should be address and then it should be data. Okay, so ALE pin, if it goes high, then you are latching with the address, that is the lower lines, that is your D0 to D7 are going to act as address lines. Okay, then afterwards, once you get the complete 16-bit address along with the higher lines, then you can access the data from that particular address. Okay, so it is ALE pin, that is address latch enable pin. Okay, so here option C will be the right answer, ALE, address latch enable. Then we'll go to the next question. In 8051 bit, addressable memory RAM area is assigned in the range of what? Okay. Now, if you just roughly remember the RAM organization of 8051, you can remember that the initial address of the RAM is given to the banks of register. Then the second part is given to the bit addressable memory. Then you will be having something called a scratch pad, and then you will be having something for SFR. Okay, so the bit addressable memory lies from 20H to 2FH. Okay, 20H to 2FH. So here option A will be the right answer. So here you can see organization of RAM, general organization. Initially you will be having from 00H till 1FH, a bank 0, bank 1, bank 2, bank 3. These are bank of your registers R0 to R7. And then you see from 20H till 2FH, it is bit addressable area, where a particular bit can be used in your application for switching or onning, offing, anything. Okay, so it is 20H till 2FH. So answer A will be the right answer, 20H to 2FH. We'll go to the next question. In 8051, when division A comma B instruction is executed, the remainder is stored in which register? Okay, so here whenever we use division A comma B, so this is division A comma B. Okay, it is as good as you're doing A divided by B. Okay, so in this case the quotient will go in register A and remainder will go in register B. Okay, so here the option B will be the right answer. Okay, so it is option B which is the right answer. Then we'll go to the next question. To access the bit addressable RAM in 8051C, that is embedded C, data type used is what? Okay, so the options here are unsigned character, S bit, bit, and SFR. Okay, so out of this, the S bit and bit, these two where you can think about which can be given to bit addressable RAM. Okay, if you're using S bit, then it is for your SFR bit addressable. But if you want to address only bit addressable RAM in 8051, then it is bit. So here option C, bit will be the right answer. Okay, so here if you see the table which is there in almost every theory, okay, if you see the S bit, that is this point, it is SFR bit addressable memory, and if you see bit, that is this line, if you see, okay, this line, if you see this line, if you see, it is for RAM bit addressable memory. So it is bit, it is the bit data type which is used for RAM bit addressable memory. So it is C bit. Okay, then we'll go to the next question. the special function register used to set the interrupt priority. Okay, so interrupt registers which are shown in the option are IE and IP. IE is for interrupt enable and IP is for interrupt priority. So it is IP register which is used for interrupt priority. So here the option will be IP, interrupt priority. Then we'll go to the next question. In 8051 special function register, that is SFR, to hold the data for serial communication is which one? Options are tmod, tcon, sbuf, and scon. Okay, now out of this, the serial communication registers are sbuf and scon, and out of this, the register which holds the data is serial communication buffer register sbuf, which will hold data before transmitting also, and it will hold data after receiving also. So here the option SBUF will be the right answer. Okay. So in 8051, the SBUF register holds data for serial communication. Then we'll go to the next question. A Thevenin equivalent circuit always consists of, okay, options are voltage source and a series resistance, voltage source and a parallel resistance, current source and a parallel resistance, a current source and a series resistance. When we studied Thevenin's equivalent circuit, we saw that it was voltage source along with a series resistance. So here if you see, it will be voltage source along with series resistance. So here you can see this is your voltage source. This is voltage source. Okay, source. And this is your series resistance. Okay, so here you can see RS as your series resistance. So this is your series resistance. So it is voltage source in series resistance, which should be the answer. So here option A, a voltage source and a series resistance is the answer for a Thevenin equivalent circuit. Then we'll go to the next question. For maximum power to be transferred from a source to load in a network, the load resistance must be dash the Thevenin's resistance. Okay, so here the load resistance must be equal to Thevenin's resistance. So option C will be the right answer. If you go to the theory, in our Thevenin equivalent circuit, the maximum power transfer theorem states that the maximum amount of power will be dissipated in the load if it is equal in value to the Thevenin's or Norton's source resistance of the network supplying the power. Okay, so here the option should be equal to. For maximum power transfer to be transferred from source to load in a network, the load resistance must be equal to the Thevenin's resistance. Okay, then we'll go to the next question. A current is minimum or zero in a tuned circuit where options are L and C are in series, L and C are in parallel, R and L are in series, and C and R in parallel. So out of this, L and C in parallel, which will give you a parallel resonance concept in which impedance will be high and current will be minimum or zero. Okay, so it is option B, which is right here, L and C in parallel, which will give you parallel resonance concept. Okay, so here you can see a parallel resonance circuit stores the circuit energy in the magnetic field of the inductor and the electric field of the capacitor. This energy is constantly being transferred back and forth between the inductor and the capacitor, which results in zero current. So it will be having a high impedance and zero current. Okay, so here option B will be the right answer. L and C are in parallel. Then we'll go to the next question. A resonant frequency equation for parallel resonances. Okay, so all these options are given here. So out of this option, option B, that is 1 by 2 pi under root 1 upon LC minus R square upon L square. That is what we have proved when we studied resonant frequency for parallel resonance. So here if you see, the equation can be proved in this way, and in the end you get that resonant frequency is equal to 1 by 2 pi under root 1 by LC minus R square by L square. So here Option B will be the right answer. 1 by 2 pi under root 1 by LC minus R square upon L square. Then we'll go to the next question. A design equation for shunt element of a constant K high pass filter. Shunt element means the parallel element of constant K high pass filter. Okay. So here, if you see a constant K high pass filter, whether it is T type or pi type, okay. So if you see, it can be like this. It can be like this. This can be a T type, or it can be like this, which can be a pi type. Okay, which can be a pi type. This can be a pi type. Now, in both these cases, the a capacitor is in series and inductor is in parallel. Okay. So if you take the impedance of inductance and capacitance, that is Z1 into Z2, which will be equal to your R naught square. Okay. So then Z1, Z2 is nothing but 2 pi FL into 1 upon 2 pi Fc, which is equal to R naught square. Okay. That means R naught is equal to, okay, R naught is equal to under root L by C. Okay. So because here 2 pi f and 2 pi f will go, so it will be L by C. So when R naught square is equal to L by C, R naught is equal to under root L by C. Okay. Now this will be your first equation. This will be your first equation where you say R naught is equal to under root L by C. This will be your first equation. Okay. And then we know that the cutoff frequency of high pass filter is given as, okay, 1 upon 4 pi root LC. Okay, 1 upon 4 pi root LC. Okay. Now this will be your second equation. Clear? Now here, in place of LC, okay, in place of C, you substitute whatever you get in equation 1. So in equation 1, if you take this is nothing but in equation 1, if you see here, this was R naught square, which is equal to L by C, and then you can write C is equal to L upon R naught square. Now this you use in the resonant frequency expression. Okay. So here, if you see, you can write this as Fc is equal to 1 upon 4 pi, okay, under root L you keep as it is, and C you substitute by L upon R naught square. Okay. So this is nothing but 1 upon 4 pi under root L square R naught square. Okay. So this is nothing but 1 upon 4 pi L upon R naught. Okay. So this is nothing but Fc is equal to R naught upon 4 pi L. Or if you want the expression for L, that is the shunt element, that is the parallel element in your high pass filter, then L will be equal to R naught upon, okay, 4 pi Fc. So this is the expression for your parallel component, that is a shunt element in your constant K high pass filter. So here you can see it is R naught upon 4 pi Fc, which is the answer here. Okay. Then we'll go to the next question. Reflection coefficient in terms of load impedance ZL and characteristic impedance Z dot. Okay. So now we know that reflection coefficient is something which is reflected voltage upon incident voltage. Now a reflected voltage can be represented as the difference between ZL and Z naught, and incident voltage can be represented as the sum between ZL and Z naught. So in that case, the constant K will be equal to ZL minus Z naught upon ZL plus Z naught. So option B will be the right answer here. So here you can see the amplitude of the reflected voltage is given as difference between the load and the characteristic impedance, and the amplitude of incident voltage is proportional to the sum of the load and a characteristic impedance. So that's why it is ZL minus Z naught upon ZL plus Z naught. So K is equal to ZL minus Z naught upon ZL plus Z naught, reflection coefficient. Okay. So we'll go to the next question. In the following equation, okay, V is equal to Vc sine omega Ct plus Ma Vc upon 2 cos omega C minus omega Mt minus Ma Vc by 2 cos omega C plus omega Mt. In this, what is USB? What is upper sideband? Okay, so whenever we see the equation for AM wave, okay, whenever we see the equation for AM wave, okay, AM wave. So whenever we see the equation for AM wave, it is Vc sine omega Ct. Okay, and then you can have plus some amplitude as MAVC upon 2, and then you can have something as cos omega C minus omega M, and then you can have MAVC by 2 into cos omega C plus omega M. Okay. Now here, the first part whatever you get will be the carrier. The first part whatever you will get will be the carrier. The second part, it is omega C minus omega M frequency. Okay, which in terms of frequency, if you see, it is Fc minus Fm. Okay, this is nothing but the lower sideband. Okay, and in the third one you can see it is omega C plus omega M. Okay, which is nothing but Fc plus Fm, which is your upper sideband. So upper sideband will be the third expression, that is MAVC by 2, and cos omega C plus omega M will be the upper sideband equation. So here you can see MAVC by 2 cos omega C plus omega MT is the right answer here. Okay. Now here omega C plus omega M, that only will give you the upper sideband. Okay. Omega C minus omega M will give you the lower sideband, and omega C will give you the carrier. Okay, so the first equation of A option is for carrier, second equation is for lower sideband, and then the C option is for upper sideband. Okay, then we'll go to the next question. A NAND gate's output is low if options are given as all inputs are low, all inputs are high, any one input is low, any one input is high. Okay, a NAND gate is a complemented AND gate. So in that case, when all inputs are high, the output will be low. Okay, so here you can see the options. Okay, in this truth table, A and B are input and Q is the output. When the input is 0 0, output is 1. When the input is 0 1, output is 1. When the input is 1 0, output is 1. When the input is 1 1, that is all your inputs are high, that time the output is 0. That means all the input should be high, then only the output will be low. So here option B will be the right answer. All inputs are high. Okay. Then we'll go to the next question. Which of the example below expresses the distributive law of Boolean algebra? Okay, so here we can, if you just observe these options, option C, that is A into B plus C is equal to A into B plus A into C, is expressing distributive law. Okay, so here you can see a distributive law permits the multiplying or factoring out of an expression. Okay, so A into B plus C is equal to A into B plus A into C. Okay, so that will be the answer here. A into B plus C is equal to A into B plus A into C. Okay. Then we'll go to the next question. Applying De Morgan's theorem to the expression ABC bar, we get. Okay. So a De Morgan's theorem, we have seen that the multiplication of a bar will be converted into individual sums. Okay. So in that case, the option A will be the right answer. If it is A, B, C whole bar, that will be converted into A bar plus B bar plus C bar. Okay. So here you can see De Morgan's first law implementation gives that A into B is equal to A plus B. Okay, so A into B whole bar is equal to A bar plus B bar. Okay, so here the first option, that is for A, B, C whole bar, the option will be A bar plus B bar plus C bar. Okay. Then we'll go to the next question. The 2's complement for 110110 is how much? Okay. So 2's complement, if you want to know. So here the number is 110110. Okay. So to find the 2's complement, we should first convert it into 1's complement. So if you want 1's complement of this, 1 will become 0, this will become 0, this will become 1, this will become 0, this will become 0, this will become 1. And if you want 2's complement, then you have to add 1 here. Okay. Then if you add 1, 1 plus 1 is 0, carry over 1. That 1 will come here. Then it is 0, then 1, 0, 0. So 0, 0, 1, 0, 1, 0 to the base 2 will be the answer. And here you can see that answer as option D. Okay, so option D is the 2's complement of 110110 to the base 2. Okay, so here you can see answer D is the option. Then we'll go to the next question. Half adder has dash inputs and dash outputs. This is a very easy question. If you just remember the block diagram or the circuit diagram also of half adder, you know that the inputs are 2 and the outputs also are 2, that is sum and carry. So for 2 inputs, you will get 2 outputs. Okay. So here the option D will be the right answer. So here you can see half adder is a combinational logic circuit with 2 inputs and 2 outputs. The half adder circuit is designed to add 2 single bit binary number A and B. It is the basic building block for the addition of 2 single bit numbers. The circuit has 2 outputs, which is called as carry and sum. Okay, so it is having 2 inputs and 2 outputs. So here option D will be the right answer. Then we'll go to the next question. Race around problem is overcome in which flip-flop? Okay. Race around problem is occurring in JK flip-flop and it can be solved in master-slave JK. Okay. So race around condition will occur in JK flip-flop and it will be solved in master-slave JK flip-flop. So race around a condition or a race around problem can be overcome in master-slave JK flip-flop. So option C will be the right answer here. So here you can see, if you see the 3 inputs for JK flip-flop, that is J, K and the clock. Okay. So the output will be like this. If J is equal to K is equal to 0 and if clock is equal to 1, the output will be previous input. If J is equal to 0, K is equal to 1, clock is equal to 1, then it will reset the flip-flop. If J is equal to 1 and K is equal to 0 with clock is equal to 1, it will set the flip-flop. But when J is equal to 1, K is equal to 1 and clock is equal to 1, it will toggle the flip-flop. Okay. Now, thus the output will be unstable, creating race around problem with the basic JK circuit. This problem is avoided by ensuring that the clock input at logic 1 is only for a very short time or to produce more sophisticated JK flip-flop. That version of JK flip-flop which will have a clock period for very short time period, the improved version of JK flip-flop will be your master slave flip-flop. So it is JK master slave flip-flop which solves the race around condition problem. Okay, so here the option C will be the right answer. Race around problem is overcome in master slave JK flip-flop. Then we'll go to the next question. A 6-bit DAC has a step size of 20 millivolts. Determine the full scale output voltage. Okay, so here you can see that it is a 6-bit DAC. 6-bit DAC means 2 raised to 6. Okay, minus 1. This should be multiplied by your step size of 20 millivolts. 20 millivolts. Okay. So 2 raised to 6 minus 1 is 64 minus 1. This is 64 minus 1 into 20 into 10 to the power of minus 3. Okay. So this is 63 into 20 into 10 to the power of minus 3. This will give you, in terms of voltage, okay, 1.26 volt. Okay, so here the option B will be the right answer here, 1.26 volt. A 6-bit DAC has a step size of 20 millivolt. Determine the full scale output voltage. So the full scale output voltage, your formula was, as we have taken the full scale output voltage, your formula was 2 raised to 6 minus 1 into 20 millivolt. This is the formula for your full scale output voltage. This is your full scale output voltage. Okay, output voltage, full scale output voltage. This is 2 raised to 6 minus 1. This is your number of bits. Okay, so 2 raised to 6 minus 1 into the step size voltage here. Okay, so it is 64 minus 1 into, so it is 63 into 20 into 10 raised to minus 3 because it was millivolts. And if you convert it into volts, so it will become 1.26 volt. So 1.26 volt will be the answer here. Okay. So students, here I have taken another 20 questions of your DCET question paper for the year 2020. Okay. So in my next video, I will take the next 20 questions of the question paper. Thank you very much.